Hmm. In previous video, we learned how to build the circuit from its truth table. Now suppose we have multiple outputs and we have a very long expression and also large number of inputs. So for each output, we have an expression in terms of the input variables. So finding the truth table itself is a tedious job. Means we will try each combination of inputs and then find each output based on that combination. So we also have a solution for this, and basically for each output we can write the expression itself to this software, and it will automatically calculate and provide us the truth table. So go to combinational analysis. Okay, then we will take two input, A and B, and output. What we can do, we can check for already known truth tables. Let's say, or these are just names. So okay, now go to expression, select the output from here, for which output you want to write the expression. So for or, okay, we have A, we can write like this, or B. So the logical expression is basically A plus B. So you see, this is equivalent to A plus B. Now we also can write this way. This also works. Or enter. This also works. Now look at the table. It has already calculated for or. Isn't it nice? Okay. So this truth table is basically correct. Yeah. Now for and, we can write like this: A and B, enter. So you see, this is AB. We can also write this way: A and B. This is basically bitwise one, bitwise and. You see, no change in expression. We can also write it this way, then also no change in expression. So all these are same basically. That corresponds to AND operation. So if you know programming language, you know what is a bitwise operator and what is a logical operator. So if we are calculating for each bit, so and this is bitwise and logical and works the same way. Now let's check the table. Yeah, for both 1 and 1, output is 1, other cases it is 0. So this is also correct. Now see for XOR operation. So for XOR, we also have a operator, that is this operator. We can basically write this way. Enter. This is XOR B, means A XOR B. In the table itself, you can verify if both are like, then output is 0, else output is 1. Now we also know that the XOR operation can also be written this way: A B bar plus B A bar. So bar is basically not operation. So we can write A not B, or A not B, or A not B. All these three are same. So I will go with this A not B. If you know C or Java, you might be familiar with this, and this expression should be a valid C or Java expression. Now A or B plus B or A. Okay. Now we don't know in which order this expression will be evaluated, whether it's A or A not B plus B not A, or A times not B plus B, we don't know. So there is something called operator precedence. If you don't know, here also we have operator precedence, and that goes like this. So first the expression with not will be calculated. So highest precedence is for not, it is not. Then the precedence is for and then for jar, XOR, that is say, and then for OR. Okay, so remember, first is not, then and, then XOR, then OR. Okay, so this expression should also evaluate to XOR operation. Let's see. This is coming a b bar plus b a bar. Now from table itself, you can check when both are alike, 1 1 or 0 0, output is 0. Other cases, output is 1. Okay, now if we want to find can of map for each of the output, we can go to minimize section. Here we can also select whether we want sum of products or product of sums. I'll go with sum of products. Okay, for which output, for XOR output, you can see this is a b bar plus this is b, this is a bar. Okay, if you know, you can find, no problem. If you know k, what is k not map. Mm, Now let's build the circuit. Okay, okay. This is main. Main is the circuit name. Use two input gates only. Yes. So you can see this is the output. And in one of the previous video, we saw this also works like XOR gate. We also verified there. So thank you. This is all for this video.